Okay, welcome to a video here on some diffraction considerations for crystalline materials. This will focus mostly on cubic systems. And so just to get us thinking about the need for distinguishing between crystal systems by a measurement approach, I'll highlight just this interesting iron system where starting at low temperatures below about 912 C, we have iron that exists in its alpha phase. So the alpha phase is a low temperature phase, which has iron atoms packed in a body-centered cubic arrangement. Once we transition past 912 degrees C, we have a phase transition, and you can see that atoms rearrange, and all of a sudden the iron atoms adopt a face-centered cubic arrangement to give us the gamma phase of iron. That gamma phase of iron is stable until about 1400 degrees C, at which point we transition back to a high temperature body-centered cubic arrangement for those same iron atoms. This higher temperature body-centered cubic is distinguished from that found at the lower temperature with a delta symbol. And finally, when we heat past 1538 C, we melt the crystalline system and we acquire a molten iron. So clearly, if we had a measurement technique, something that could distinguish the type of crystal structures present, body-centered versus face-centered cubic, this would help us characterize this material as it undergoes its transitions. And this can be used to characterize other materials, including those that are not cubic as well. Okay, so to understand some of the concepts for diffraction, we need to think about the wave sense for radiation and its properties. So waves are known, either waves of fluid like water or waves of radiation like light, to add to one another through a process called interference. And that interference can either be additive or subtractive, or in other words, can be constructive or destructive. So should two waves traveling through their media have their peaks aligned and their wells aligned, they will add and the amplitude will double. As you see here, this wave is twice as tall as the two separate waves prior to interference. However, if these waves are out of phase, where peaks are not aligned, and in perfect misalignment, that is, the peak of one wave is aligned with the well of the other, we see that continuing here, we will get the condition for perfect destructive interference, and the waves will cancel. And so there'll be no resulting wave. This is emphasized in some physics labs. Things like speakers need to be connected correctly to make sure their poles, their positive and negative terminals, are connected correctly. If one speaker is inverted, the sound quality drops remarkably because the sound waves coming from the speakers are in opposite phase, and a lot of the quality of the sound will be canceled. Okay, so with that idea, you may have observed diffraction before in everyday materials. Here's a classic physics experiment where diffraction from a compact disk is quantified. And so here you see the simple idea of putting a compact disk acting as a diffraction grating, and owing to the reflective aluminum that is found in a compact disk, the incident light that travels onto the aluminum would at least be expected to bounce straight back towards a laser source. But something additional happens in that the diffraction grating, that is the little features within the disk, sets up conditions for constructive interference at certain angles. Okay, so these special angles here are where constructive interference has been satisfied, and we can diffract and maintain intensity at the board here in this case, where the light has added and created intensity at the board. In between these angles, there's destructive interference, and no light is found at the board. So in the diagram here, we are seeing the first order diffraction from a green laser imposed onto a compact disc, and at higher angles, diffraction is also possible, and that's not found in this photo. It's not emphasized in this photo, but it can be seen in other experiments. Okay, so in other words, the incident light onto the compact disc can give a first order constructive interference diffraction intensity at the board. And we'll see that matched on both sides with the same alpha, or same angle theta, I should say. And at some angle later, theta 2, for example, we can get a second order diffraction condition satisfied, constructive interference there, and we can build intensity at the detection board should it be large enough. Okay. So what we've seen here is that the features of, there's something special about the features on the compact disc, and we'll see here that the properties of the incident radiation in this visual case here, the wavelength of the light, are going to come into the equation to help us understand the angle at which we would expect constructive interference and a diffraction intensity at a detector or cardboard surface like we have here. Okay, so just to formalize this, diffraction is radiation scattered by a regular array of scattering centers whose spacing is about the same as the wavelength of the incident radiation. So if this is green light, approximately 630 nanometers in length, we know, because we are seeing diffraction, that the features on this compact disc must be on the order of the same wavelength. So these should be approximately 600 nanometers in periodicity, because our incident laser has a wavelength of approximately 630 nanometers. Okay, so that's how we interpret that. And not only is the feature about that size, we expect a regular array of those to be able to satisfy the condition for diffraction. Okay. Now, the electromagnetic spectrum is made up of all sorts of different types of radiation. We've just taken a look at a specific visible light case with a green laser pointer of about 630 nanometers. We also know that other types of radiation exist, and you can see not too far along is the X-ray category. So X-rays are smaller in wavelength, approaching 1 nanometer often in their size, and this is on the order of the features that we see in our crystal systems. That are the distances that we've been calculating for our unit cells, which describe the periodicity of our atoms in our crystals. So it's a great achievement to have been able to sort of devise a device to take advantage of this and ultimately lead to an instrument called a diffractometer that uses X-rays to quantify and study the lattices that are present in crystalline materials. Okay, so as we recall, the diffraction gratings must have spacings comparable to that to the wavelength of the incident radiation to be diffracted. And so if we're going to use X-rays, we need things with periodicities on the order of 1 nanometer, and that is very close to the packing distance between atoms in crystals. When things get very, very small or very large, away from the X-ray radiation's wavelength, we will not see any diffraction, because again, we're mismatched between the wavelength of our radiation and the features that are periodic in our material. Okay. So putting those ideas into place, here is a cross-section diagram of an arbitrary lattice of atoms. You can see a row of atoms here with a black line representing connectivity between atoms, perhaps bonds, and the next sort of row of atoms below. So this could be, if it was a perfect cross-section, this pattern could continue behind the page and in front of us. And of course, it could continue deeper into the material as well. We're going to see that we'll impose an incoming radiation, in this case X-rays, because their wavelength, crest to crest distance, so green crest to green crest, that wavelength is on the order of approximately 1 nanometer, and the distances between rows of atoms is about 1 nanometer often. So we've satisfied one of the requirements for diffraction, in this case by way of diffracting X-rays. Now, as an incoming source of radiation strikes, say, a row of atoms with electrons and atoms, it's natural to think that the radiation, which has both electric field and magnetic field components, would undergo a reflection. And so we see that first beam 1 getting reflected and going towards a detector, as we saw before in the previous case, a cardboard some distance away from the sample, which is a compact disc. In this case, we need an X-ray sensitive detector to quantify the amount of intensity at the certain spot on the detector. Because incoming radiation is often large in its kind of source, so we have wide and many parallel beams of monochromatic, the same wavelength radiation of X-rays coming in, we can expect a neighboring ray of X-rays to come in. And it may travel between the first and the second layer of atoms as it sort of interacts with an area between atoms and passes to the next area. And so that's what we see here, is that a parallel beam of X-rays may penetrate deeper into the sample and travel further, therefore. So that extra distance that ray 2 has had to travel is important. It's gone an extra distance here, shown in pink, before it found the next atomic layer that's available for a reflection, and then it'll do the same extra distance there. So the pink, as shown in this diagram, is representative of the extra distance that arbitrary ray 2 has had to travel relative to the distance traveled by ray 1. And this is an important idea, because if we want to be able to satisfy constructive interference, that extra distance has to be a very special amount of distance. If it's too far, we may set up destructive interference. If it's too short, the same. But if it's just right, crests will realign with crests, and wells will realign with wells between these parallel incoming X-rays. Okay. So clearly some of the angles upon which we impose our radiation onto the surface of the sample are important. So we'll be using theta or theta C for that. And we've seen that the parameter, in this case, the distance between planes, given symbol DHKL, is another important feature here for satisfying the amount of extra distance traveled and how important that is for satisfying constructive or destructive interference. Okay, so these are some important features that we're going to see in our derivation of a law that will help us predict when constructive interference will occur. Okay, so taking another look at that setup, we've seen that the incident ray may come in with angle theta relative to the surface of the sample. Okay, so there's our sample. Okay, and it's going deeper off screen. We have two incident beams again. On the previous slide, we had extra distance pink here. And if we examine the sort of geometry and the triangles in this area, we can calculate the extra distance. So some conditions for understanding how theta transmits into the triangles established by point P, S, Q, and T are reflected in this diagram up here. Our incident radiation was meeting the surface at angle theta. Because this is a right angle, moving to between the incident beam 1 and incident beam 2, we look at that right angle. And we also know that there's a right angle made between planes of rows of atoms. It follows, therefore, that theta, the angle incident for beam onto the surface of the sample, is also matched into here by this logic. So theta plus x must equal 90 is a consequence of how we've set things up here. So that was right here. Theta plus x must equal 90, and x plus y must also equal 90. So by solution, y must equal theta. Okay, so there's one feature there. And so we see that reflected down here now in our first triangle. Theta, that angle there. Similarly, on the neighboring triangle, we have an extra theta there as well. And then we saw that this was a right angle triangle, and we have a hypotenuse right down from atom P moving to atom Q. And so we'll use that and the sine law for those right angle triangles to help us. Okay, so extra distance SQ and ST was important for helping us understand whether or not we would expect constructive interference. So it follows that if lambda is a feature of our incoming radiation and we want constructive interference, the only way we would expect that is if the extra distance SQ plus QT is an integral multiple of the wavelength of that light. Okay, so that is n lambda must equal that extra distance. So if that extra distance is just one full wavelength, that's perfect. N would equal 1, and then we would be back into alignment between peaks from beam 2 with peaks with beam 3. If it were 12 equivalents of the wavelength of the radiation, that would work out. We would have the 12th peak realigning from incident beam 2 with incident beam 1. Okay, if n is not integral, we're going to drop the intensity of diffracted light at the detector. Okay, so and a perfect n that is at a half integer, so that is 0.5, 1.5, etc., is satisfying the condition for full cancellation of beam 2 by way of constructive interference with beam 1. And we would see 0 diffracted intensity at the detector positioned out here. Okay, so with that logic, we can then consider some sine laws for these right angle triangles down below. And we know that the distance PQ is the hypotenuse. And of course, the small angle in here, shaded in red now, is theta. And so the sine of theta represents the distance SQ. And so sine theta is equal to SQ, and the distance PQ from this point here to here is, of course, our distance between planes, the D between planes abbreviated with Miller indices HKL. So that value is right here. Distance times sine of theta is going to equal the SQ piece. And of course, we're going to add that to the distance between planes with Miller indices HKL times the sine of the same theta, which is going to represent the QT piece. Okay, and of course that's the extra distance, and that must be equal to n lambda. So rearranging this and simplifying the equation, we end up with what is called Bragg's law, which is n lambda is equal to 2d sine theta. Okay, d is of course specific to the set of planes we're considering, and it will be different for every set of planes that might exist in a crystal. Okay. So that's Bragg's law. N lambda is equal to 2d sine theta. And we'll see some other requirements for how we interpret this condition for diffraction and the use of Bragg's law in a moment. Something to say here is that theta, in order for this form of Bragg's law to work, we want to be using radians for the theta. Okay, so be very careful on whatever calculator you're using. If you're using your graphing calculator, by simply hitting the mode button, you can access a window where you can switch between radians and degrees. And make sure that if you're using Bragg's law that you input in radians. You can also calculate radians from the equation that 1 degree is equal to pi divided by 180 degrees. Okay. So with the fundamentals in place now, we can consider the instrument a little bit. So we saw we were going to take a radiation source, a wide beam of all the same wavelength of the incident X-rays is going to be imposed onto the sample. The sample will have a surface which helps us establish the angle of incidence, also called the Bragg angle, theta. And we might expect that if the sample plane was continued and the beam was allowed to pass right through the sample, the path of incidence is here. And so we have, of course, this angle here as our incident angle, theta, again. Okay, and so the architecture of instruments is often to place a detector for monitoring for constructive and destructive interference as beams are reflected out of the sample, is to position that at the same angle, at the Bragg angle. So here you see the detector from the plane of the sample, it has been moved to an angle theta up away from the plane of the surface. Okay, and so for historical reasons, the graphing that results, the data that results from X-ray diffraction, is actually defined as an x-axis that is the 2 theta. So it's the angle between the incident beam path swept all the way through to where the detector is. And that represents the x-axis coordinates for our information. Okay, so shown a little bit better here is that as we try to sweep and acquire data, that we're expecting the x-axis of our graph to be 2 theta as we consider moving the detector through a range of 2 theta values for the sample. Okay, so the detector will sweep angles at a rate that matches the X-ray source sweeping in the opposite direction. Okay, and then our collectors, of course, monitoring the intensity of detected X-ray intensity, and that might give us peaks and low intensity and peaks, provided that we satisfy Bragg's law. Okay, so in other words, here's how the process might go. We'll collect a set of intensities, so we'll monitor data, and until there's Bragg's law satisfied, there'll be no intensity of detected light at a certain 2 theta value, again, where the incident beam would be relative to where the detector is. Okay, so 2 theta is here. And once Bragg's law is satisfied, then we'll build intensity at the detector, and then as Bragg's law is unsatisfied, then we'll return to almost baseline intensity, very little, just background intensity at the detector. And then once Bragg's law is satisfied again, perhaps we'll get another peak of intensity in our X-ray diffractometer. So here we have the position 2 theta generated by the mechanics of moving the X-ray source and the detector sweeping towards each other through lots of options for 2 theta, and then monitoring the amount of intensity for the X-rays at that detector. Okay. And then through either tabulated information and what's known for certain materials, we could identify planes detected, so identify the D values from Bragg's law ultimately by solving for Bragg's law, solving for D, and then deducing what planes must be responsible, and we'll see that in a moment. Okay, so here's another data set just to sort of enlarge things. This is the data set for powdered aluminum. Here you can see we're specifying now what incident radiation was imposed onto the powdered aluminum. So it was a lambda of X-rays corresponding to wavelength 0.1542 nanometers, so very small wavelengths on the order of the distance between atoms. And here we see the various planes that are responsible for satisfying Bragg's law and allowing us to detect diffracted X-rays at the detector. Okay. Good. So some other kind of requirements for Bragg's law. So again, Bragg's law was n lambda is equal to 2d sine theta. And some other requirements for parallel planes of atoms with a spacing that is the same of h, k, and l between those planes, we want to see destructive interference when we satisfy the equation above, Bragg's law. In most diffractometers, the incident radiation is fixed. So in the previous example, we saw copper K alpha, which was equal to 0.1542 nanometers there. So that is a constant. So far, the left-hand side is looking constant. As we know, crystals are often very large and include very many sets of unit cells, and so we'd expect many planes of atoms next to each other. And so we have families of planes that may diffract only at a very specific angle, theta. A requirement for the geometry of the conditions for incident radiation and where the detector is in our sample is important here. So the plane normal must be parallel to the diffraction vector. Okay. So a diffraction vector here is defined by the following. So a plane normal is the direction perpendicular to the plane of atoms. So here in the diagram above, that would be the dotted line. That is our plane normal. And now, what is the diffraction vector? The diffraction vector is the vector that bisects the angle between the incident and diffracted beam. Okay, so that's also right there. Okay, so those two must be parallel, of course. If they're not, if the angle of incidence and our lattice was not as shown, but on angle. So I'll try to draw that. Those black lines here now like this. You can see that the plane normal is not parallel to the diffraction vector. And so those are no longer parallel, and we would not satisfy the condition of our instrument and allow for detection at our detector. Okay, so hopefully that clarifies it. So clearly something important about how the planes are oriented relative to the sample. Okay, just clean that up so we can see the corrected version there. Okay. And as we've seen before, just to reemphasize, the spacing between diffraction planes helps us determine where the peaks would be located in our XRD graph. And the peak intensities are a consequence of several things. we would expect at the very least what atoms are present in this sample. So if we have very large atoms packed very closely, we're going to be very efficient at scattering X-rays towards the detector. If the atoms are very small and far away, we might expect just a lower intensity at the detector, even when Bragg's law is satisfied. Okay. So to emphasize that earlier point about the plane normal being off angle from the diffraction vector, we show that here. So in the case where a single perfect crystal, in this case a garnet ruby, is studied, we have perfect planes of atoms all the way through this crystal, all the way through. It's a perfect crystal. And so in the case of the 1, 0, 0 plane and the family of those, we would satisfy this requirement for the diffraction angle being parallel to the diffraction vector being parallel to the plane normal, and so we would expect intensity there. Bragg's law would tell you that you should find an intensity here at around 29.5 degrees 2 theta, but because our plane normal is off angle from our diffraction vector, which bisects the angle of incidence from that where we have our detector, that we will not see the predicted 1, 1, 0 because the sample planes are not aligned correctly. So if we could rotate those somehow, then the 1, 1, 10 would grow in. Likewise, for the 1, 1, 1 and the 2, 0, 0 is also now satisfying Bragg's law, and the diffraction vector is parallel to that of the diffraction vector. The plane normal and the diffraction vector are parallel. To solve this problem, engineers and scientists will often granulate their sample, make a powder out of it. This helps create a layered material full of many tiny crystals that are randomly scattered throughout all options in their orientation in the layer of sample, as you sort of see depicted here. So this could be the same sample just ground up, made into a powder. And this allows us to reposition random pieces of crystals throughout the sample. This would allow families of planes, like that represented here by the 1, 1, 0, to now have their plane normal parallel to the diffraction vector. And now this satisfies the requirement for detecting those Bragg's law predicted intensities, in this case at the 1, 1, 0, and we also see the 1, 1, 1 present as well. Okay, so powdered samples give more information in X-ray diffraction. Okay. We mentioned briefly that the sets of atoms is responsible for how high these peaks are. And the next piece we'll consider here is that the peak intensity is also related to how many planes we have available to help us with the diffraction. So in other words, how big are these crystals? If that red crystal there is very large, we have many sets of planes, and so the crystal size being very large helps us have enough sets of planes to build intensity at the detector. But if it's very, very small, only a few sets of planes, we don't have enough density of planes of atoms to build us intensity at the detector. So the peak intensity is not only related to the type of atoms involved, but it's also related to the extent of crystallinity of a particular plane. Okay? So how far sets of planes, for example, if we could extend the lattice, which we know is represented by the unit cell, and we could extend this very, very far, the set of 2, 0, 0 planes here would be very deep into the sample, and we'd expect large intensities here. If the sample was very short, we didn't have a lot of crystallite present, that is this dimension before we go to a different orientation, a different crystal with a different orientation, or to a boundary of the material, then the intensity is going to drop. Okay, so there's an equation called the Scherer equation, which helps describe how the idea of particle size or crystallite size is related to the peak intensity or in peak shape. So here's our lesson here. For sharp, well-defined diffraction peaks, like these shown here, we can apply the Scherer relation. Okay, so if particle size lies between 0.1 micrometers and 40 micrometers, we can apply the Scherer equation. And when crystal sizes are large, less diffraction occurs. And then as smaller sizes are found for crystals, we're going to expect peak broadening. Okay, so let's spend some less diffraction. So that's going to make it very sharp. Okay, so the peak width is what we're talking about, very sharp. And if the crystals become shorter and shorter, so this one in here, if we shrink that down smaller and smaller and smaller, we're going to broaden that peak, and we'll see wider peaks as a consequence. So X-ray diffraction can provide an estimate for the crystallite diameter, symbol tau, via the Scherer equation. Okay, so left-hand side is the crystal size. It's about the crystal is estimated to be modeled as a spherical structure. That has limits, obviously. And the right-hand side is a shape parameter, K. Okay, so this is a constant. If we consider spherical type crystals, then the shape parameter is 1. And if more oblong crystals are considered, this can adjust to about 0.9. Gamma is, of course, the wavelength incident on our sample, so it's specific to the instrument. We saw copper K alpha used a moment ago. And beta here is called the full width at half max. So we have a maximum value, and if we go to the halfway point, okay, where this intensity here, it matches this value here, so let me put I and I there to equate that. We go to the halfway mark, and then we measure how wide that peak is. The width of that peak at half of its maximum is beta. Full width at half max is equal to beta. And then we're going to put that cosine of theta here. So theta is, of course, the angle of the primary diffraction peak. So here we have 2 theta at 47.351. We would input theta in radians into the Scherer equation. Okay. Very good. So up until this point, we've been thinking just of planes of atoms, but as you might remember, there are atoms between certain planes, like in the body-centered cubic unit cell. There's a set of atoms in the middle of every unit cell. In face-centered cubic, there's sets of atoms at the center of every face. And so this sets up some additional rules for X-ray diffraction if we consider those sites as well. And without deriving the set of rules, here's how we interpret it. So for a BCC, a body-centered cubic system, we would expect diffraction when Bragg's law is satisfied, and when the set of planes that we're considering, the H, K, and L values from the Miller indices, add to an even number. Okay, so for example, a 1, 0, 0 plane adds to an odd number, and so this is not satisfying the condition for a body-centered cubic. So we would not expect intensity there. Let's go to a BCC data set and examine if a 1, 0, 0 is present, and it is not. A 1, 1, 0 set of planes adds to an even number, and so that does satisfy the diffraction rule, and we would expect to see a 1, 0, 0 if satisfying Bragg's law, and so that would tell us where to find it on 2 theta, and we can see that shown there. So in other words, in a BCC data set, the peak intensities, the Miller indices for the set of planes that led to a certain DHKL for Bragg's law, those HKL values should all add to an even number. So 3 plus 1 plus 0, even. 2 plus 1 plus 1, even. If it's odd, we saw that example, we will not find the diffraction plane and the intensity in the XRD. Okay. In face-centered cubic, the rules are similar. However, so you see that reflected here. Mixed and unmixed is what's used in your textbook. And how we interpret that is that in order for a reflection to be observed for an FCC system, the HKL indices must all be odd or all be even. Okay, so we can look at the aluminum, the indices H, K, and L for the set of planes that we're considering for diffraction. They have to all be odd or all be even. So 1, 1, 1, all odd, we're okay. 2, 0, 0, all even, we're okay. 2, 2, 0, we're okay. 3, 1, 1, all odd, we're okay. And so those are the rules for a face-centered cubic system. Okay. Some additional rules are known for the hexagonally close packed system, which we've touched on periodically. And so we'll just sort of skip past that. Okay. So as we start thinking more about the Miller indices for the set of planes that we're considering for our diffraction planes for Bragg's law, we've seen that they're involved in satisfying conditions for intensity in our X-ray graphs, our X-ray diffraction graphs. And clearly they must be related to the distance between planes of atoms. And so an equation has been developed for that for cubic systems, as we show here. So for cubic systems, the unit cell dimension A, which is of course representing all dimensions of the sample of the unit cell, is the numerator, and if we divide through by the square root of the sum of the squares of those Miller indices, this is how we calculate D. So of course our numerator has a dimension in, say, units of nanometers, and if we were talking about the 1, 1, 1 set of planes, our denominator would be 1 squared plus 1 squared plus 1 squared is of course 3, and so root 3 would be the denominator in this example. And if we knew the A value for the unit cell in question, then we could predict what the 1, 1, 1 interplanar distance would be. Okay. And we saw that in Bragg's law we had n lambda is equal to 2 DHKL sine theta. So we now have more understanding for D, so we could input that here and actually express Bragg's law, if we needed to, in terms of a unit cell value, A, and its HKL values. So some questions may demand that strategy. Okay, so let's recall, we've been spending quite a lot of time understanding D and theta. We saw lambda is often constant, depends on what radiation we are using to study our matter. And we have N, which is the order of the diffraction. As we saw in our early examples for light on a compact disc, we could diffract to a first order angle, which was the nearest intensities away from our reflection or our source. And we'd expect second order diffraction as well. So that is the identity of N. And so for most data sets, we consider an N to be 1. And in many questions that you'll see, you'll be given this information, what the order of reflection is. If it's not specified, you can assume it's N of 1 and move on. Okay. Okay, so you can see hopefully that the technique is very useful for helping us distinguish between very similar atoms and packed structures of those atoms, and even ionic type compounds. Here's oxide of iron. So we have hematite, the hematite form, and we have the magnetite form, and their formulae are different, and clearly their XRD patterns, the pattern at which for where we find diffracted X-rays, is very different. So this is a bit of a fingerprint for material as you needed if you're tasked with trying to identify a crystalline sample. Okay, so let's take a look at an example here, question, where we're asked to investigate body-centered cubic iron and compute the interplanar spacing and the first order diffraction angle for a 2-2-0 set of planes. We're also given the lattice parameter, so this would be A, and here we have the lattice parameter value is 0.2866 nanometers, and we're given the X-ray radiation that was used, so 0.179 nanometers is lambda, and we're also told that the order of the reflection is 1, so this is our N value. Okay, so in order to address part A, we need to calculate the interplanar spacing. So our equation for that was DHKL is a function of the lattice parameter A divided through by the square root of H's value squared plus the K value squared plus the L value squared. Okay, so for this question, our numerator is the 0.2866 nanometers, and the denominator is going to be the square root of 2 squared plus 2 squared plus 0 squared. And so our denominator will be the square root of 4 plus 4. So root 8, and then our same numerator, 0.2866 nanometers. So notice that I've been able to just work with nanometers directly in the numerator, and I'm going to inherit an answer here that's in nanometers because our denominator is unitless. And so after doing this, you should find an answer of approximately 0.1013 nanometers as the distance between 2 to 0 planes. Good. Okay, and then we're asked to find the diffraction angle . Okay, so let's tackle that part next. Part B. So we have Bragg's law is equal to n lambda is equal to 2d HKL sine theta. We are asked to find the first order diffraction angle. So solve for sine. So sine theta is equal to n lambda over 2d HKL. Okay, so from our previous part A, we have the denominator information now. First order, so that was 1 times the wavelength used for the experiment. So in this case, we're asking to consider 0.179 nanometers in lambda. We're going to divide through by twice the distance between planes for the 220. So we calculated that a moment ago, and that was 0.1013 nanometers. Okay, so this fraction should be 0.884. Notice we are unitless. Okay, so not degrees, unitless. So when one is in a unitless outcome at this point, you know that you must handle this as radians. Okay, so as you take the inverse sine of this, once your calculator is in radians, you will find that theta here is equal to 62.13 degrees after converting into from radians to degrees, using the fact that 1 degree can be found as doing pi divided by 180. Okay. So this is theta, of course. Our X-ray diffraction graphs put this as 2 theta. And so we need to determine the position on this x-axis where this peak would be. So once we have that, our final step is to simply double it, and 2 theta is going to equal 124.26 degrees, and that is going to tell us the x-coordinate for the expected diffraction intensity peak here. Okay, so take a minute to try that on your own. Practice your radians to degrees. That was very important in this problem here. And that's it. Thank you.